Alright, let's think about another momentum conservation related example. So this time, let's say we have two molecules coming towards each other. Let's say that they're floating in air and they're moving towards each other. So molecule A has a mass of micrograms, B has a mass of, molecule A has a mass of 2 micrograms, B is 3 micrograms. Velocity of A is 10 millimeters per second, B has 5 millimeters per second. Now they're coming towards each other. This is before the collision. Now they're going to collide at some point, right? They're coming towards each other. And then after collision, let's say the two molecules creates a bond and becomes like a one big molecule, A and B combined. So we want to find out whether it's moving. If it is moving, which way it's going, what's the velocity. So we don't know what's happening after the collision, right? So we can use momentum conservation, that principle, momentum conservation principle, to find these velocities after a collision like this. Okay, so here in this example I am using different units, like we are used to have kilograms and meters per second, but it's a good thing to have some practice with other units as well. So this needs a little bit more conversions here and there. So the first thing I would do is actually try to convert all these into standard units. So 2 micrograms is 2 times 10 to the negative 6. This is 3 kilograms. Microgram, milligram, hold on, nope, not really. So 1 gram is 10 to the negative 3 kilogram. 1 milligram, 1 microgram is 10 to the negative 6 grams, therefore it's 10 to the negative 9 kilograms. Okay, let me double check before we go any further. Yes, it's 10 to the negative 9 kilograms, so need to change this to negative 9 over here. 3 times 10 to the negative 9 kilograms. Millimeters per second. Now millimeter is 1,000th of a meter, so therefore this will be 10 times 10 to the negative 3 meters per second. This will be 5 times 10 to the negative 3 meters per second. Alright, the reason I prefer to use large objects in this example is we don't have to deal with all these 10 to the powers, but once in a while it's a good practice to go over these things, because these are the real applications you will be dealing with in your advanced research, right? All these small masses and smaller velocities. Okay, so we have everything converted now. So let's say they collide and they form a bond, and we don't know which way it's going. So let's just take this is the velocity final to the right, and let's just call it just VF. Now it's gonna be common to both of them. They're both gonna move together, so it's just one velocity. Let's call it V final. If we get a positive answer, that means the direction we marked is correct. It's moving this way. If we get a negative answer to our final velocity, that means it's gonna move in the other direction. Now you guys know we have to define a positive direction, right, in momentum. So we're gonna take this as the positive direction. Okay, so let's try momentum conservation. It says momentum final, the total momentum. We can actually put a sigma in the front to indicate the total momentum of the final system is equals to the total momentum of the initial system. Now, total momentum of the final is the two masses moving together. So we have to find what is ma plus mb. That is our mass, which is 5 times 10 to the negative 9 kilograms, right? So we can write 5 times 10 to the negative 9 times Vf equals momentum initial. So that is momentum of A plus momentum of B initial. Momentum of A is its mass times velocity. B is going in the other direction. So in the equation you have to consider that, right? There's a directional difference. Alright, so the mass will be 2 times 10 to the negative 9. Velocity is going to be 10 times 10 to the negative 3. Vb is going in the other direction, so if you put a plus here, and its mass is 3 times 10 to the negative 9 multiplied by negative 5 times 10 to the negative 3, because it's going in the opposite direction. Okay, so we have 5 times 10 to the negative 9 Vf equals, what do we have here? 20 times 10 to the negative 9 times 10 to the negative 3 minus 15 times 10 to the negative 9 times 10 to the negative 3. 20 comes from multiplying these two, and then negative 9 and negative 3. 15 negative comes from multiplying this and this and the rest of the numbers. Now you can see that this cancels out all the 10 to the negative 9s. We have 5Vf equals 20 times 10 to the 3 negative 3 minus 15 times 10 to the negative 3 gives me 5 times 10 to the negative 3, but this is a positive 5, 20 minus 15. Vf is, divide to the other side, 5 and 5 cancels out, 1 times 10 to the negative 3 meters per second, or you can say Vf is 1 millimeter per second. This is a positive number. We didn't get a negative sign in the front. That means the final system, this AB combined, the big combined molecule, is also moving in the same direction like VA, because it had more momentum than B. So the final outcome should be in the same direction with the bigger momentum and moving with a velocity of 1 millimeters per second, or 1 times 10 to the negative 3 meters per second. Alright, so this is another type of an example where two things coming towards each other, different, the momentum directions different. So when you get the total, you have to actually, mathematically it's a subtraction because one is negative. So I just want to show you guys a kind of different example. Okay, let's move on to another one. Another common type of momentum examples involve a situation like this. Imagine firing a rifle. So here's the rifle barrel. I'm trying to draw a rifle here. Okay, so here's the rifle. So before firing the rifle, now the rifle has a bullet inside, right? So it's a small metal bullet inside. Now when you shoot the rifle, when you fire the rifle, what happens is the bullet comes out, and if you have experience with this, you know that the rifle is kind of going to jump backwards. We call it the recoil. These recoil velocities, now I take rifle as an example, but the same thing applies in many other systems where you have one big entity breaks into two smaller participants. So in this case, the rifle and the bullet is our initial system, and once you fire it, bullet goes in one direction, the rifle is recoiling backwards. So these are the secondary smaller participants, right? So in a chemical reaction, it could be splitting of a big molecule into two smaller pieces. It could be a radioactive decay process where the mother nucleus breaks into two daughter nuclei. It could be a division of a cell, and you want to find out how fast these pieces are moving, what directions. So all these things can be understood using momentum conservation. So here we take the example of this rifle and the bullet. Now let me put some numbers into this. Let's say the mass of the rifle, this is mass of the rifle, mass of the bullet. Let's say rifle is 5 kilograms. The MB is, let's say, small 0.2 kilograms. So this is like 20 grams. And when you fire it, let's say the velocity of the bullet, which is really fast, it's going to be 600 meters per second. Question is, what's the recoil velocity of the rifle? So once you fire it, what happens is you have this same rifle here, and we have a moving bullet. Now the rifle recoils backward. So this is the bullet, the rifle. So we can use momentum conservation to find this VR velocity. Now we take this as our initial system, this whole thing with the bullet inside the rifle, nothing is moving, right? The whole thing was stationary, it wasn't moving. Now we have two separate entities, two separate pieces, the bullet and the recoiling rifle. So this is our second system, and this system has velocities. So we can say, so this is the initial system, and I'm going to say the momentum of that P initial. Here's the P final, momentum final. As always, we can write P final equals P initial. Momentum final. Again, if we take this as the positive direction, we have the bullet which has a mass of 0.02 times a velocity of 600 plus the rifle with a mass of 5 kilograms with a velocity of VR. Now I have marked it in this direction, but I'm without worrying about the negative sign, I'm just going to write it like this. We might end up having a negative answer. So this is the bullet, this is the rifle, which is equals to P initial. Now what is the initial momentum? The bullet was just sitting inside the rifle, it wasn't moving. Rifle wasn't moving either. So the mass of this thing is the total of both, but the velocity is 0, means the momentum is 0. So now we have O2 times 600 plus 5 times VR equals 0. So I can take this to the other side. 5 VR equals negative 0.02 times 600. VR is negative 0.02 times 600 divided by 5. Some 2.4. Let's see what it's exactly. I get 2.4 meters per second negative. So the recoil speed, the rifle is going to jump backwards, recoil at a speed of 2.4 meters per second. The negative sign tells us that even though I wrote this as a positive number here, it's a negative velocity, means it's moving this way. If I have a positive number, that means it's going in the positive direction, like the bullet, which is impossible, which won't happen. It should go in the other direction all the time. Because how do we, so to justify the answer, initially the system didn't have any momentum. So the final system, whatever the momentums it has, they should cancel out each other. So if one component going in x direction, the other component has to go in the negative x direction, vice versa. If there were no momentum in the beginning, there can't be any momentum in the final system, so that means the participant should cancel out each other's momentums. Okay, so the rifle has to recoil backward. That's another example. Similar kind of ones, firing a cannon. Another one would be somebody jumping off of a boat that was floating, like stationary, not moving anywhere. You jump off of the boat recoils backward. So there's so many things you can think of. Okay, all right, let's move on. Okay, so the next topic I want to discuss is, it's called impulse. Now this is also a widely used quantity related to momentum. Now let's see what impulse is. Now you already know that there's a relationship between force and momentum. Force equals delta momentum divided by time. We talked about this earlier. We talked about this in class. This is another way of defining Newton's second law. Force equals momentum change divided by time, delta P over T. Alright, so let me rewrite this way. Delta P over T equals F. Same thing, yes? I'm going to multiply both sides by time. So I'm going to multiply this side by time, this side by time. See, this and this cancels out. I have delta P equals force multiplied by distance. Now this is pretty much the same thing. I'm just manipulating terms in this equation. But once you write it this way, we have a new name. This combination, this product, force multiplied by time, is called impulse. Sometimes we use the letter I for impulse, sometimes we use the letter J for impulse. So either way is fine. So impulse is force times time, force multiplied by time. Also, it's the change in momentum. You can have momentum, you can have a change in it. That we call an impulse. We can find it by multiplying force and time. The symbols are I or J, so the unit's gonna be same as units of momentum, which is kilograms meters per second. That's the unit. And most of the time impulse is used to indicate large forces applied within a short period of time. So that's, in a practical sense, that's when we use the term impulse, right? If a force is being applied in a very short time, we say that it creates an impulse. But in general, it's just force multiplied by time. Okay, so we can write impulse equals force times time. If you are in the calculus class, if you are in the university physics class, you should know the other definition as well. Impulse can be written as the time integral f dt, force times dt in a given time interval, right? So that's another way of writing impulse. Okay, so let's see what examples we have. So this time let's talk about few conceptual type examples. We know that impulse change in momentum is given as force times time. Think about a situation where somebody get into an accident driving a vehicle and some collision and the airbags deploy. So what's the purpose of airbags? How it prevents injuries or try to prevent injuries? So when the vehicle is moving, right, so it's going this way, there's a person sitting inside. Person also has the same velocity as the vehicle. So the person has, if this is going at 70 miles per hour, the person inside also going at 70 miles per hour. And then you come to a rapid stop, a collision. So the speed of the 70 miles per hour becomes zero in a very short time interval, right? So there's a huge momentum change. So same for the person, he was traveling at 70, now comes to a stop very rapidly. That rapid deceleration can cause a lot of damages, internal injuries. So that's the momentum change. You have to bring this momentum, this initial momentum, it comes to zero immediately. So this product remains the same, right? This is momentum change. The momentum changes from this speed, whatever momentum you had earlier, to this, zero. So if we can increase the time, we can decrease the force that is associated. That's what airbag does. It still brings you to a stop, but with a relatively larger amount of time. Imagine without airbags, you hit against the steering wheel or something, you come to a stop immediately, right? But with the airbag, it slows you down, it gives you more time. By increasing the time, you decrease the force. So impulse remains the same, but by allowing it more time, you can reduce the force. So that's kind of one way of explaining force-time relationship associated in momentum. Another example, I kind of mentioned this in class. When you jump from a height, let's say you're on a rooftop and you want to jump back to ground. When you land, now don't try this, but when you land, automatically you bend your knees. So when you're coming down, right, this is the ground level, this is you coming with your legs extended maybe, so you're coming with some velocity, you have some momentum. The moment you hit the ground, like split second later, your velocity becomes zero. So there's a large momentum change in you. Delta P is really large. You're coming with some high velocity and you have your mass, so you have an initial momentum, now it becomes zero. By bending your knees, you allow more time for yourself to slow down. So again, you increase the time, you decrease the impact from the force, right? So these are a couple of practical situations I thought you'll be interested instead of doing math all the time. Okay, so let's move on. All right, let's talk about collisions one more time. Now you know that for an example, let's say we have two masses coming towards each other. Now this is one of the examples. There can be one mass is stationary, the other one moving towards it, or it could be they both going in the same direction but one is faster than the other. So the collisions can happen in many ways. So let's just take one example, one of those where they coming towards each other. Now this is the situation before collision, they're moving towards each other. Now after the collision we can have two scenarios. One is they collide and then bounce off of each other, right? So A and B collide, and then A and B going in opposite directions. Another scenario could be they collide, and then like in chemical reactions, like two molecules or two atoms coming towards each other and form a bond and becomes one unit. So it could be the whole thing either stops, they come from opposite sides and collide and form a bond and just sit there, or maybe as a single unit they'll be moving in some direction. So these are different outcomes of a collision like this. And we also know that regardless of the outcome, whatever that P initial is equals to P final, or P final is equals to initial. So momentum is always conserved. When it comes to momentum, P final is equals to P initial. It's conserved all the time. When you measure the mass and velocities of initial side, compare it with mass and velocities of final side, they match up. What about kinetic energy? Now we talk about energy conservation, where there's a conservation between the energies, kinetic energy and potential energy. When we disregard friction, we see that they match up. Even there's a difference. When you account for the frictional losses, the energy conserves. Now in a situation like this, two things come in towards each other and make a collision, and then either go in opposite directions or going the same direction. Let's say they all happen in the same level, whether there's no potential energy differences. As long as they all move in the horizontal direction, we don't have to worry about going up or down. So there's no potential energy involved. Or even if things are moving in different directions, like up or down, the moment of collision, like just before and just after, they're pretty much at the same spot. So we don't really have to worry about potential energy part. The question is, what is happening with the kinetic energy? Do we have a kinetic energy or an energy conservation? If you think about the kinetic energy of incoming particles before collision and kinetic energy or kinetic energy of the system after the collision, are these two things equal to each other? Is there a conservation? So that is something we can investigate. When it comes to collisions, there are two types. One type is called elastic collisions. The other type is called inelastic collisions. Based on the kinetic energy, or energy conservation, we can divide collisions into two. Remember, regardless of what kind of collision, momentum is always conserved, elastic and inelastic. But when it comes to kinetic energy, in elastic collisions, kinetic energy conserved. Kinetic energy loss. There is an energy loss in inelastic collisions. Later we can divide them again into partially elastic and partially inelastic. We're not going to go that far. I just want you guys to know that there are two types of collisions. Based on what happened to the kinetic energy, we're going to separate them into two groups like this. Elastic collision means whatever the kinetic energy you had before is going to be the same kinetic energy after the collision. It's kind of difficult to find real world, large scale examples, things we can see clearly with our eyes. Sometimes, like, in the game of pool or billiard, those collisions between pool balls, closely elastic, still you hear them hitting each other, right? This always generates some noise. That means some amount of energy is changing into sound. There's a little bit of a loss. But if you go to the microscopic world, most of the time collisions between molecules, atoms, are mostly almost 100% elastic collisions. They don't lose kinetic energy in a measurable way. Inelastic collisions. Most of the collisions we see around us, let's say two vehicles collide, mostly inelastic. Most of the time they lose energy in the process. If two molecules or if two objects come towards each other, collide and become one entity, connect to each other, that's most of the time is an inelastic collision. Okay. Alright, so let's work on one or two examples. Okay, so let me erase this real quick. Most of the examples we will have are inelastic collisions, so I will try one of those. So in this case, let's say this is a railway track and we have this railroad car MA, the mass of it is 10,000 kilograms. It's moving at a speed of, let's say, 25 meters per second, and we have another one, an identical one here. It's not moving, it's at rest. This is B, same mass, so A and B both 10,000 kilograms. Now after the collision, let's say they're gonna stick together and probably they will move in the same direction with some velocity, we don't know. Question is, how much energy was generated in this collision? Energy generation. Now, what do we mean by energy generation? The collision you can definitely hear like a loud sound, right? So that is some of the initial energy transferring into sound energy. It can generate a lot of heat in these collisions. That's another way of losing energy. So how do we find this? We can start with momentum conservation, because we know that regardless of the type of collision, momentum is conserved. We don't know about the energy conservation. Most probably there is no energy conservation here, so we can't start with that. We have to start with momentum conservation. And why momentum conservation is so useful? Now think about solving this problem using kinematic equations. We need to know how much deceleration for the initial car. It's coming at a high velocity, it's going to lose that velocity, right? It's going to slow down. So we need to know what is that final velocity and how long it took to drop this velocity. What's the distance it traveled during this slowing down process? Was it a constant acceleration or was it a changing acceleration? We don't know any of those. And then the second car, it's going to speed up. It was initially at rest. So how much time it took to speed up? Was it a constant acceleration or not? So there's so many variables we have to deal with if we don't have momentum conservation. Momentum conservation just looks at the initial and final states. So as usual, we say that this is initial, this is final, and we can say PF, PI. The combined system 20,000 kilograms going at V is equals to initial 10,000 going at 25 plus 0. The second card didn't have any momentum. Alright, so straightforward answer. Cancels out, cancels out. V equals 25 divided by 2, 12.5 meters per second. So the final system is going to move at a speed of 12.5 meters per second. Now we got that final velocity using momentum conservation. Now let's look at the energy side. What is the initial energy of the system? E initial. Cart A has half mva squared, which is half times 10,000 times 25 squared, which is a large number, 625,000 divided by 2. Let's see. So I have a pretty big number. I'm going to write it in kilojoules. 3125 kilojoules. Let's find E final. Half times the combined system, which is 20,000, 12.5 square. What I get is 1562.5 kilojoules. Clearly a difference, almost like half of the energy has gone away, right? So the energy loss E initial minus E final, 3125 minus 1562.5. Okay, I have to do it again. 3125 minus 1562.5. Oh, half of it. That much energy it's gonna lose. Alright, so there is this is definitely a inelastic collision. If there's an energy loss, if the final energy is less than initial, it's a inelastic collision. Okay, so we will work on more examples like this.